when the opcat proposal started kind of getting real, it was posted to the mailing list, and it was limited to 520 bytes. And I think I was probably not the only person who said, why are we limiting it to 520 bytes? That seems kind of limiting, because with opcat, script gets more interesting. As script gets more interesting, we're going to start to bump into that. And there are good reasons why, of course, it's limited. And you go back through the history of script. In 0.3.2, Satoshi did this kind of emergency release where he just amputated a giant pile of script, and that's what everyone knows as script today, right? So, opcat was gone. A whole heap of string operations like left, right, multiply was gone, divide was gone. What else? Integers were limited to 4 bytes mostly. Prior to that, they hadn't been. Left shift and right shift were gone. The whole heap of opcodes just got thrown away, and everything else kind of got truncated, probably overzealously. But I understand, like, the network was in danger of falling over. I mean, you could there were no restrictions on this, right? It was using the big num library in OpenSSL, and it was literally coded as openly as you could imagine, right? So if you said, hey, here, push 10 billion on the stack, and then like a left shift to 0 by that many bits, you would get to keep both halves of the network that was broken. So so a whole heap of stuff was thrown out, and other things restricted. And of course, we start to bump up against those restrictions now. Most obvious being opcat. People are like, all the wonderful things we could have if we only had this. But there are a whole pile of other ones. So I started looking at if you were looking at fixing this properly. And I feel like almost Satoshi, understandably, just roped off whole rooms of the house and went, don't go there, right? But we've kind of been living without a kitchen since then, and it would be nice to have it back. So what would beyond the emergency response, what would like a planned response look like? Obviously, there needs to be some limit on what opcodes can do. There both needs to be size limits because of RAM constraints, but also performance limits, right? How slow are these things if you start to get really big amounts? So I kind of looked at this question. I went, well, we already have kind of a solution that we used for signatures, right? Originally, there was just a limit. I think it was actually the same release that Satoshi put in the 20,000 like Sigop limit, which was kind of approximately per block, which has been refined to a per weight signature limit of 80,000 ish. But that Sigops budget kind of provides us with a model for what would like a general variable length operations budget look like, right? Which I call varops. So based on the weight of your transaction, I'll get to that in a sec, you get a certain amount of budget, and various operations use up this budget, and if you go over budget, you're screwed. Now the reason that the Sigops budget works so well is because you can show fairly easily that since the signatures of reasonable size, you will have a 64-byte signature somewhere for every reasonable Sigops check you can do. So the fact that it costs, you have to have 50 bytes of witness somewhere to pay for your Sigops is not a problem, right? It's not a problem that you hit in real life. So you have a very clean divide. You've got this limit, but the ceiling is high enough that you're never going to hit it in real life, but low enough that it stops a denial of service problem. So the question was, can we use a similar thing to do a generic? You can push much larger things on the stack and add them together, or them, or hash them. What's a reasonable limit? And so I set out to kind of answer that question. And the early explorations around that were the basis for my talk in Austin at BTC++. So that's kind of where a very rough heuristic on where we come to. You end up with ideally getting rid of some of the other limits and folding them in. So for example, you can pretty much fold in a Sigops limit. Once you've picked your numbers, you can figure out, well, okay, this gets me this much Sigops. There are a few tricks though. If you bring back all the opcodes, you have some fun ones. The ones you really end up having to care about are divide and multiply, because these on extremely large numbers can be slow. And you care about left shift, or as I call it, up shift, because left shift is a really weird term, or L shift, as the opcode is called, is a really weird term when you're actually little endian, because a L shift moves you right. So I call it upshift. But then also, obviously, that has to be limited too. You can't just, shift your number and then go, oops, that was too big. It didn't fit in memory. You need to check beforehand. But pretty much every other primitive in script is pretty well constrained already. So as long as you have a limit on both your total stack size and your stack element limit, you can put an upper bound on how slow things can get. So since then, my work has been pretty much running a whole pile of benchmarks across different machines. I got myself a Raspberry Pi 3. I'm not going back before that because I'm basically assuming 64-bit machines. So that was a reasonable lower bar. A Pi 3, I have a Pi 4, a Pi 5. I have, interestingly, you can't compile Bitcoin Core on a Pi 3. It just doesn't have enough RAM. So actually I have to compile on the Pi 5 and then copy the binaries across. So it really is the lower limit of usability. I feel pretty confident about that. I've got my laptop, which is an Intel machine, and I've got like a few years old, not super high end. And I have my build machine, which is an AMD machine, which is also a few years old, but was pretty high end at the time. So, but I'm not really caring about high end machines. I'm really concerned about low end machines because obviously, if you can create a block that is ridiculously slow to mine, that's bad. If it takes 30 seconds to validate a block on a Raspberry Pi, probably nobody cares because your miners are not running those. If it takes more than 10 minutes, of course, that's a threat to the network. If you can keep it under a couple of seconds for this, there are obviously other ways to make blocks that are expensive, but I'm at least trying not to make the problem worse by introducing this. So, so there's been a whole pile of nasty benchmarking that's been going on as I kind of wrestle with the question of how much should all this stuff cost. Cool. So I'm going to pause at that point. Have I given you basically a overview of what's happening, what I'm trying to do, or what I'm thinking about at least? Are you still listening? Okay, I'm getting thumbs up icons, which is pretty cool. I didn't know you could do that. And also, I'm going to take that as silent acknowledgement. Okay, so right, so benchmarking. I proposed, based on my early benchmarks at BTC++, that we basically use a cache model, right? How many cache lines do you touch for each operation? And basically, that's how much you pay. Further benchmarking revealed that does not actually map well to performance. Unfortunately, it's kind of a nice model, but there are better models that you can come up with. In some ways, simpler. Basically, while you have to confirm this across a variety of machines, the model that I've ended up with at the moment is that there are basically two kinds of operations: fast operations and slow operations. There are a handful of fast operations. Comparing two things is quite fast. And comparing something with zero is quite fast. And that's important because converting something to a value, which we do in a couple of opcodes, is also basically a subset of that problem. Those are fast. I did have zero fill as a fast operation, but I can show you some cool graphs showing that was a dumb idea. And everything else is slow. So, and basically, fast operations cost 1 per byte and slow operations cost 2. Obviously, there are some operations that have multiple passes. So multiply being the classic, right? And divide. They've got a square factor in there depending on the size of your operands. And so you can formulate them as multiple passes for the worst case. And it's all worst case thinking, right? So add, for example, subtract. One change that I did propose was that we drop signed, the whole concept of signed integers. Most people don't use them anyway. They do introduce problems. It's hard to mix Satoshi just got them from OpenSSL. So the way integers work in script at the moment is the high bit is the sign bit, which means that you can accidentally have something flip to sign. So you've got to actually basically prepend a 0. That's how even our current opcodes, which only take 4-byte inputs, can produce 5-byte outputs that then they can't consume, which kind of shows you some of the ugliness of the amputation that occurred. So I went, you know what? No, we're just, I asked a mathematician, they said they were unnatural. So we're going for unsigned numbers. I think I made that joke in my talk. So unsigned numbers only, and that simplifies things, but it has some interesting side effects. So subtract is illegal if it underflows. If you really care, if it's really possible and you don't want it to fail, you should test beforehand. But it also means, for example, subtract is twice the length, sum of the length of the operands in its cost, because it's a slow operation, so it's 2 times. Whereas add is 3, because add can overflow. And that may involve, right at the end, you go, crap, we've got to copy this thing. And copy is a fast operation, so that costs 1 extra. So you have to take into account the worst case, add costs 3. And that applies to some other, other interesting cases as well. So you do end up with some kind of stranger costs. I can show you a benchmark I completed just yesterday, because I thought, oh crap, if I'm going to talk about this, I should get back and try to scrape some time out from my real work, working on the Core Lightning release, and try to hone my benchmarks. So I have a pure series of micro benchmarks across all the different operations you might want to do. But importantly, the focus of my benchmarks has been increasingly to actually run real scripts through modified Bitcoin Core, so that you get all the gore, right? It's not this idealized micro benchmark, but actually running 10,000 instructions of something and see what that comes out as. So I think I can share my screen, which I should be able to do. Find the button. Let's try this. Entire screen. Okay. You should see yourself for a moment, ideally. Oh, yeah, there we are. Okay. So this is actually, I haven't labeled the axes, sorry. Here is a whole heap of a pile of different opcodes. And my current approach is to have a total stack limit of 8 megabytes and a per element limit of 4 megabytes. And the reason for that is that I really just like some of the numerology. People pick numbers all the time, pull them out. But given that our block size is 4 meg, if we had an operation that could do introspection and would dump the whole transaction on the stack, it would logically be limited to 4 megabytes. But in any stack-based language, having a single copy of something doesn't get you anywhere. If you want to do any surgery on it, you usually have to make a copy to do something. So hence, allowing 2 of them seems a reasonable upper bound. So I've gone, okay, you can have 8 megabytes on the stack total, which means for most evaluation for Bitcoin Core, you'll need 12 megabytes, because at some point, you make copies temporarily, so you'll need 12 megabytes. Nobody cares. Nobody cares. And, machines are so fast now and so big, no one cares about 12 megabytes. But this is an attempt to measure, like, what's the worst case of all these different opcodes, and you can see them here. These are all the opcodes for which size matters on the stack. So we've got all the re-enabled opcodes, we've got hashing opcodes down the end. And this is then divided by the cost. And the cost for the hashing opcodes is 10 times the number of bytes, empirically based that number. For most of these, it is 2 times, although some of them are a little bit more. Now, you'll notice that these first two, op equal and op equal verify, are shockingly expensive, right? They're really out of line with the kind of numbers you see on the others. This is for good reason. So I mentioned before that I had fast operations, and I considered zero fill to be a fast operation for my micro benchmarks. So the classic zero fill is taking an empty object, an op0, and left shifting it or up shifting it by 16 million bits, right? That basically just fills it with 4 meg. So in a handful of opcodes in re-enabled script or stored script, you can get your 4 meg object on the stack, right? You don't need to carry it around with you. You can make them really easy. You don't have to even opcat them together. You can make them pretty fast. And that operation itself is very fast. The problem is that what you generally end up with, and seem to end up with in this implementation certainly, is 4 megabytes of cache called data. So these scripts are actually they start with 2 4 megabyte objects on the stack that are fully equal, so that equal will do the worst case. They do an op equal, but then in order to chain them, I have to restore them. So I did push 16 million on the stack, push 0 on the stack, push 16 million on the stack, do an upshift, and then dump it. And it turns out that it seems that I was getting cache called data out of that, and that was meant the next operation was much slower. So these times for op equal and op equal verify are distorted, and this is where micro benchmarks can be quite misleading. And this is the reason why I wanted to benchmark real instructions here. So while op equal and op equal verify are not slow, doing them on something that we have just pulled out of cold cache can be. Now, of course, intelligent machine would do something clever and reuse the data a lot, but I'm really interested in the worst case, because it's the worst case that people may end up being able to trigger, and that's the case that sets our baseline for how much operation we can do. So you can see from that I am probably going to be making zero fill an expensive operation, so make it at least 2 times like everything else, a slow operation, and stick with comparison things being the fast operation, and that will bring those down by a significant factor. So they will still be up there, but they will not be ridiculously, over twice as expensive as every other operation. You can see here there's some kind of interesting ones. Opcat is what you'd expect. Here's op add and op overflow about under the letter G there. Op add overflow is basically when you take what exactly was the number? I think it was I add 2 numbers that basically 2 FFs actually, both of which are 3,999,999 bytes long. And so it overflows to 4 megabytes. Obviously, you'd have to make them smaller because it would be illegal for them to be larger than 4 megabytes. And similar with the op add, we basically take take that and reproduce it there. So these numbers need some revision because I'm going to play with the weights of the refill parts. Op divide. There is a worst case for op divide. It's very perverse. And I have to actually sit through the algebra to figure out exactly what it is. So these op divides are ridiculously cheap. You can't even see them on here once they're divided by their cost, but the cost is the worst case cost. So I have to figure that out. And everything else is not really a surprise. Hashing is, as you'd expect, so on different machines, hashing is different. The Pi 5 does SHA-256 really, really fast. It's shockingly fast. Whereas this laptop's fast at most things, but relatively SHA's slower. But so to give you an idea, I basically took the slowest of the slow operations and the slowest of the fast operations and went, well, this is the ratio. This number works. Based it on how long does it take me to check 80,000 signatures, right? So actually do a Schnorr check sig, sorry, not the operation, actually just do a Schnorr verify on 80,000 signatures, right? Because that's kind of the upper limit today. How long does that take? Okay, you've got that long. How much work can you do in a block? That's slightly unfair. It's slightly unfair because we actually parallelize Schnorr signature checks. But on the other hand, there's a lot more than just checking the signature. There's hashing and other things in there. So, it's at least a benchmark to base it on. And I wanted to make sure that number, kind of that worst case number was not exceeded by the worst case thing you could do with varops introduction. And I've also written a little tool that I will release when I clean up my really, really messy C++ code, where you basically feed it a script on the command line, and it will tell you, it uses an approximate, it basically figures out, it's supposed to tell you what is the largest stack operand that you could provide it for it to exceed the budget, right? So, or in the perverse case, the smallest. And if it's over 4 megabytes, it goes, well, okay, you can never, this script can never exceed its varops budget, right? And that is really important for my base case here, which is that if we can come up with the limits correctly, and if the numbers work, which it seems like they do, then the varops problem is not something you will ever have to worry about, right? It's not, well, let me flip back to wherever you are. Ideally, we should be able to have most scripts look at them and trivially evaluate them and say, this can never reach the varops limit, right? That would make me much, much happier, right? There are, of course, perverse cases. If you take 2 numbers from the stack and multiply them, or divide them. But if you're multiplying by a fixed constant, my script is smart enough to go, well, the last thing you pushed was this value, so I know that's what you're multiplying by. The other thing, of course, is left shift. There's always, if you take 2 things off the, input, that left shift, you could make a really large thing on the stack. But most cases, you're doing things by a fixed operand that you've got in the script, and my evaluator's it's clever enough to figure that out. And it's actually pretty hard to come up with something, certainly something reasonable, that comes anywhere close to using up the number of varops you've got. It's the numbers that I'm using at the moment are 5,200 varops per weight of the transaction. 5,200 is borrowed numerology, right? It's because the largest current stack element size is 520 bytes. And because I charge 10 varops budget per hashing byte, that means that the most expensive thing you can do on an existing stack size thing would cost you 5,200. And the opcode itself, being weight 1, basically pays for that. So you can fairly trivially prove that any script today will run under this regime without hitting the varops budget. That's not particularly interesting, but it is a kind of a useful point. And those numbers were pretty close to the conservatively below the limits on the main machines I benchmarked, except for the Raspberry Pi 3, but the Pi 3 kind of sucks. There was about line ball for that. So yes, in summary, and I have a draft BIP that I have to update and release once I've got once I've decided on my left shift weights. Yes, we end up with a system where it's actually quite hard for you to reach these limits with anything that you would want to do in script, which is really useful. But you do get a lot of power. I mean, if you're throwing around 64-bit numbers, it's really easy. Even bigger numbers than that. You have a lot of capacity. I mean, 5,200. I mean, even though most ops are costing you like 2, that's still 2,600 bytes of crap per opcode, right? And that's some pretty big operands that you're putting in here. And the reason that the limit, by the way, is per transaction and not per witness weight. So the Sigops limit is basically the weight of the witness. So it's your witness script plus anything you put on the witness stack to start with, basically. In our case, I went, no, it's actually going to be a transaction-wide limit. And the reason is that I'm assuming that at some point we get introspection. So you will be able to, in some way, inspect or deal with data from the other inputs. And in that case, if you're a fairly simple script, like a vault script that's looking for other scripts that are also coming from the vault, and you're basically looping, you're obviously open coding your loop, but you're going through them all. The fact that one of them is huge that you have to deal with shouldn't mean that you run out of varops, right? Because you might be quite a simple script, and they might have some. You could have some, almost 4 megabyte monster sitting on one of the other inputs. So hence, it makes more sense for the budget to be per transaction and not per input. So in my talk, I did go a little bit further and say there are things we probably want because they didn't exist before when Satoshi, made these changes in 2010. We probably want some way to tweak things so that we can do effective inspection of taproot outputs and things like that, so that we can actually create, hey, is this script, I can give you the script and you can show that it's in this taproot output for this other thing. So there are a few other things that we want, but not a huge amount. And it gets us a very long way, it seems. Cool. Okay, I am going to pause there and take a breath. Oh, cool. Someone opened their hand, raised their hand. Great. If I could see who that was, let me see. Oh. Okay. First, I'll look at my messages because I did not have that window open. Okay, how consistent? Oh, this is a good question. The cost 1 versus 2. How consistent is that? It's not very. I mean, the faster ones are faster, but some of the slower ones are not that much slower. But it does hold. So you basically go, well, you can beat. I have no problem really if you beat these benchmarks, right? Most implementations will. Actually, every implementation will. To get the benchmarks, I turned off turbo and basically try to get really, really consistent machine, which is not representative of what happens when a block comes in. You're analyzing it in 2 seconds. You'll probably run a lot faster than my benchmarks do, and that's okay. You can always beat the benchmarks. That's not the problem, right? It is in some extent it's like, oh, wouldn't it be nice if we had a little bit more budget? But our budget is so excessive, our capacity is so great that I have real trouble foreseeing anybody running into these limits or having to care. So I'm not going to put a huge amount of engineering effort to kind of bump them up even more. So what happens if you're slower is that you just take the worst case. So I've taken the worst case of the fast operations and the worst case of the slow operations and gone, okay, assume that all slow operations cost this, even though they don't, and all fast operations cost this, even though they don't, right? And that's the numbers that I'm basing it on. So then you go, well, now double the fast one, and whichever one's the maximum, that's your case. So you simplify again that way. So the fact that the 1 and 2 are not reflective, it's different on different machines. For my laptop, I think the best to worst was, oh gosh, I've got numbers here. Let's see, for the Pi 5, the best to worst is like a factor of 3. Sorry, the fast to slow is a factor of 3, whereas the Pi 3, it's like 2.3. And for my laptop, it was also 2.3. And for my build machine, it was 1.7 because it was really fast. So you end up artificially penalizing the slow operations in that machine are not actually that slow, but we will treat them like that. But yeah, there was definitely a gap across those, which makes sense. And it turns up in some, actually, one of the fun things, it turns up in some fun places. So I said comparison and copying are the two. The reason is most of them use SIMD instructions on these machines, right? So everyone optimizes memcopy and memchur, basically, or memcomp, right? These two are the cases that everyone, the first thing anyone does when they're writing a library is they optimize those cases to use, like, SSE, AVX, whatever, Neon on ARM. They tend to be really fast. They do nice cache tricks. They do all these things to get themselves streaming as fast as possible. And one thing that happens in a few cases in script is that we treat a thing on the stack as a number. Left shift does it, substring does it, downshift, like, right shift does it as well, of course. If does it, right? Although if is special because it's already minimal, but there's a number of other cases that treat it as a Boolean. And if it's 4 megabytes long, you may have to look through the whole 4 megabytes just to check after the first byte, because that's really significant. We're a little endian here. So you grab the first byte, and then you just got to check that the rest is zeros, and that could be 4 megabytes long. But there's a neat trick that I probably didn't invent, but I think I'm the first one of the first people to document it anyway, where you basically, to check something 0, you check the first one 0, and then you just memcomp against itself, right? And you just compare the rest of it that way. And that's already optimized for you beautifully. So it turns out to be kind of the optimal way of doing it. So comparing for 0, which you actually end up doing in a few cases, is exactly equivalent to the comparison case. It's actually slightly more efficient because the cache, you only have one cache line, you're dirty. So yeah, these cases are all generally really fast. And the other cases, we actually probably pull data into the CPU and do stuff. Now, you could definitely get faster, right? You could write add in SSE, probably, maybe, and do fancy things, and that's fantastic. But I have assumed that you don't do that. You can probably also get faster by, I don't know, not using arrays and using some kind of rope data structure, so that when you cat things together, you don't actually just naively copy them and append one to the other. You can build a tree or whatever you want, right? But the data model assumes that you're just doing dumb stuff, right? And I think that's fair. It also was useful because I didn't have to. Basically, the budgets were still so generous that I didn't hit the point where I think, we really should optimize this. That said, my implementation does turn everything into 64-bit accesses. So there's some tricks in there so that you not doing things byte at a time, because that does make a big difference when you're looping through data a byte at a time versus doing 8 bytes at a time. That has an impact. So that's definitely worth doing. So it's a relatively optimal implementation, to be fair, but it has not gone for machine specific gross hacks to get there. Now, and the reason is that I don't think that's actually required. I don't think most of these things will be used in practice. You have to be guarding against the worst case, but I don't think people are going to be throwing around 4 megabyte objects on the stack in Bitcoin script. They're just not. So optimizing for that case is silly. And if someone starts doing weird and wonderful things like RSA and things, then at that point, optimizing those opcodes will be fantastic and no loss. So, but yeah, I'm certainly not going to make those assumptions as far as the costing model and the proposal goes. Cool. Okay. Well, I think I have kind of run out of the obvious things to say, but I am happy to answer anyone's questions. Stefan, I think you're up first then.
Yeah, just to continue on, because that's my chat question as well. Is it a fair summary to say that, so you've measured all these operations on different machines, you've assumed the worst case for each operation based on kind of the worst performance on these machines. Then you've made sure that doing those operations on the full block would not be slower than current maximum block validation time. But then, even though you say that the budget is generous enough for kind of any realistic scenario anyway, so we don't really need to have the distinction between fast or slow anyway, but just kind of as a gesture of goodwill, you added the fast versus slow. You could be adding more categories, but there's just no need for it. Is kind of what I'm getting.
Yeah, well, there's fast, slow, and hash. So hashing is 10 times, right? It costs 10. That is definitely like that measurement is, there's definitely a significant lag there. You're doing a reasonable amount of work, even with optimal implementations. And for the other hashes like SHA-1 and RIPE-MD, I'm like, you can't. It's illegal to do those bigger than 520 bytes. Like, what are you doing? Get a life. So those are not varops. They're outside the system because you can't do that today. So it's like you're not losing anything. And I don't expect anyone to have optimized those. Whereas everyone has implemented SHA-256 optimally because, of course, it's used everywhere in Bitcoin, right? So it's a reasonable assumption to benchmark those and goes, cool, that's what we're doing. There's not going to be some architecture out there that goes, wow, because if their SHA-256 is slow, they're screwed. It's not. This is what's going to hurt them. Their whole Bitcoin system is just going to run slowly. So so basically there's 3 categories. I've thought about dropping the fast versus slow things, but the common things are fast. And I kind of wanted to recognize that. But yeah, I may go back and go, you know what? Let's drop that. It makes everything artificially more expensive, but it would be okay. Gloria.
Yeah, makes sense. Thanks.
Hello, thank you. I have, maybe it's like a basic question. I'm not really, are you aware of maybe kind of the reasoning for those opcodes existing in the first place? Are they like a common scripting language type opcodes? Because I think the framing to me when people say like, oh, like Satoshi wrote these opcodes and then disabled them and that sucks. Kind of there's like almost a magical, like, oh, Satoshi must have been like correct the first time or was correct the second time. You know what I mean? It's kind of like treating his original opcodes as like sacred. Whereas I mean, like alt stack, for example, makes no sense to me. Maybe I'm just ignorant, but it's like, is the scripting language originally perfect? I don't know.
Okay, so that is a very good question. Satoshi, I can't remember where Satoshi stole it from. I mean, there's a lot of different simple stack-based languages, but someone did say it had remarkable similarities to someone that one had found, right? So he definitely did basically rip an existing stack language and chuck in a couple of check Sigops, which is why they're weird. They're not really like the rest of the scripting system. They do a lot in a single opcode. Satoshi, if he was really inventing it from scratch, probably would have done the whole like checksig is basically extract transaction, hash transaction, and check signature against the result opcode, right? He would have split those out and he would have been, okay, well, here's the transaction selection thing, and here's the hashing thing, or maybe you roll those into one because there are reasons that you don't want something that big on the stack. So you go, cool, let's hash these parts of the transaction thing, and then a checksig would have done a checksig from stack, which is completely redundant wording because of course from stack it's a stack-based language, except it isn't. The checksig we have currently is this thing that's been landed in the middle of the opcodes. So it was definitely derived from other things, right? I mean, then there were kind of obvious things to do with a stack-based language, but it was very unlimited. Like it's beautiful. Like the original code is so simple, like so exploitable, but it's it's a thin wrapper around the OpenSSL big num primitives, right? He just went, right, that's how he got the integer format that Bitcoin has, with like the high bit set to mean negative, right? It's not because he thought really hard about wanting negative numbers. It's like that was the OpenSSL big num representation, right? So didn't think too hard and just basically implemented all this simple stack machine. I do feel like, in my mind, I would never have implemented it this way, right? I would have gone, wow, what I'm building is complicated enough. I'm not going to put programmable money in here. I'm going to have check sig and maybe a check multi-sig. And you can have oracles for everything else, right? You'll have a signing oracle that will obey some, whatever, hash the script in here somewhere, and you feed it the script and it evaluates it and it signs off and all those things. I would never have put a scripting language inside Bitcoin. But I'm not Satoshi. I wasn't thinking like, I would be furiously thinking, what the hell? Like, this is complicated. I'm going to drop it. But but then I'm relying on a third party again, right? I may get to pick my third party. I may have multiple third parties, but he was really trying to design something where this programmable money idea, where the money itself was programmable, was kind of one of the core ideas that kind of led to Bitcoin and was floating around at the time. And he actually really tried to implement this. But the reality of engineering is, like, when shit is on fire and your whole network is about to explode, anything that is not obviously safe, you rip out. I have been through that experience, and I do not cast any blame at all. You can fix it later, right? But if your whole project dies because the whole thing fell over for a week, you won't get that chance to fix it later. So I definitely don't criticize the choice to radically amputate. But I do, because especially now, because I've spent so much time trying to figure out how you would do this a different way, and you have to think about everything. It's really time consuming. To look at every opcode and go, how much could this cost? What is the worst case for this opcode? How bad is it, right? Particularly now, because we don't just go, we're just going to drop another library in here, right? Obviously, all these things have to be open coded in Bitcoin itself. I can't just go, well, I'm going to use libgmp or something. Libgmp is fast. Like, I seriously went down the rabbit hole trying to figure out how their multiply was so fast, and decided I didn't need to, but it is insane. It's just ridiculously fast. So, if we could just link against other libraries, that would be amazing. But, modern Bitcoin, we basically have to have everything at our fingertips under our control. So it is quite a demand to do that.
Thank you. That's really interesting.
Cool. Plus, alt stack is really, really important as your scripts get bigger. Very few people in Bitcoin have played with serious script. It's a real art to getting stack-based languages working. It's a weird mind thing. But when you do start to get complicated, once you've got these things, you start to want your alt stack to stash some stuff. Otherwise, it ends up way too far down your stack, and you have to get it back all the time. So having an alt stack is actually it's a thing.
I see.
There's a purpose.
Have we seen alt stack used?
No.
In the wild? Okay.
No. And I can say, I'm saying that confidently, blithely. I mean, possibly, but no. Script is just not interesting. Like, it is so hobbled. It's amazing. It's people have managed to do stuff that they have without, like, with the stuff that's left. It is not. We have not got the programmable money that people envisioned in any way. So, yeah, some of the stuff is left, but you. It's kind of frustrating. On the other hand, building stuff in script. So when I built those tests, for example, I had to build something that put the thing back on the stack, restored it to wherever it was. And it's nasty to build things in script. It really is a very assembler based kind of. I was having flashbacks to my Z80 days as a student. So I can see why people want higher level things. I know maybe simplicity or something, blows all this effort away. But as far as like restoring what we had, I don't think we really. There's so much other stuff going on in Bitcoin, right? There's so many other cool things that you can build that I'm not surprised it's taken us this long to really start to miss the fact that we don't have a full scripting language. But I'm immensely confident that if we did have it, we would have some really whacked up stuff by now. Some of which will be terrible, but some of which will be great. So I kind of really want to see what people would do if they could really express what they wanted to with their own UTXOs. Nicholas?
Yeah, thank you for the talk. Have you worked on implementation yet? I'm guessing you have, because you have all these benchmarks.
Oh, yeah. I felt that I had to kind of seriously implement it to get that far.
Is there
also just to find out?
Well, my actual question is just what that looks like. Is it like are you integrating that into the core interpreter, or is it basically a second interpreter?
No, I put it straight into the core interpreter. Now the core interpreter is incredibly ugly. I get that. It has scar tissue where people have been afraid to touch stuff. It has macros in it. I seriously wanted to just take the whole thing across my knee and rewrite it, but I have resisted, on the theory that could be done as a separate project if somebody wants to do it. I've tried to keep the diffs relatively small. There are some nasty things. For example, checksig add, or checksig add. I think checksig add. The taproot one takes a number. Well, it takes a number that's a signed number at the moment, right? And obviously, with this version, it would have to take a version that's not assigned, that's a raw number. You don't want to have, oh no, for this opcode, it's using the old style numbers. You really want it to all switch across. So there are some changes which are nasty for those reasons, but I have open coded them. There's no hidden stuff. It's very much if this version. One thing that hasn't been decided, originally I was like, well, obviously this will be a new ChapScript version, or this will obviously just be a, new SegWit version. But others are like, no, there are other ways of doing this. And so I've left that. So I've basically hacked from interpreter.cpp down. So you basically, that's where you hand in, here's the version of the script you are to interpret. And that's all changed, but there's no way to create a Bitcoin transaction that ever sets that flag. So I can write benchmarks that call into that and do stuff, but there's no activation logic. There is no block format and things like that to create such transactions. Because the stuff I needed was the implementation. But I do think it's important to actually implement the whole thing, so you can actually, get benchmarks, not just in theory, but in practice. And there's some stuff, for example, opt-up, which I didn't really need to touch. I did need to touch because it currently makes 2 copies. Because it doesn't it doesn't use a reference. It's like simple missing ampersand. It makes 2 copies. And with 520 byte objects, who cares? But when you're talking about 4 megabytes, you care, right? It just gratuitously makes a local copy to dump the next copy. So it's 2 copies instead of 1. Stuff like that in the interpreter, which is weird because in other places it uses references. Like it's not foreign, it's just that one was missed. So you only find out those things when you actually implement the whole thing. So yeah, that was important for benchmarking. How would it work? We can do anything through an oracle, right? If you trust the oracle. Both of you send something, you sign to the oracle and say, this is how I want you to run this transaction. This UTXO even. You can do it all outside Bitcoin, right? And it would just co-sign anything that met those requirements. Each oracle could have a different scripting system. I mean, you could do anything. It'd be a trusted oracle, right? But it would be an oracle. And I would outsource the whole problem of how to, a fine-grained control of your money to all we will do is check signatures. And if you want something fancier, you get someone to sign under certain conditions. That's basically what it is. Does that answer your question?
Well, I guess it does, but then I'm confused about, because having trusted oracles seems like a very different model than having scripts where you don't need trusted oracles. So it wouldn't be an equivalent approach, right?
No, not at all. I would have gone script. I'm not putting a fucking scripting system in this prototype. Like it's such a complicated system already. I would have balked at doing any kind of programmable money. I would have gone like, look, you get signatures, you get multi-signatures, and sort it out amongst yourselves, right? And we almost got that, right? I mean, because script is so hobbled that there's so, it's always really tempting to fall back to assigning Oracle to do anything complicated. So yeah, we almost got the worst of both worlds. We got the complexity of script, but we didn't get the power that we were promised. So yeah, but just from an engineering point of view, I would have launched Bitcoin 1.0 without script, which, so I think Satoshi said, like, if we don't put this in now, we're never getting it. And that was probably the right call.
Yeah, fair enough. Okay, thanks.
Yeah. And it wouldn't be a very different system because that's actually what most people use. They use, like, for the first 10 years of Bitcoin, it was all like single sig, maybe a couple of multi-sigs, right? So how different would it have been really? You do need some limited scripting for Lightning, that's true. But most of it's just pre-signed transactions. Yeah.
Another, I guess, more observation and question. So it seems like what GSR is doing a really helpful job at is eliminating the DOS vectors by quantifying everything through varops. And it feels to me like that's even orthogonal to the question of which opcodes are we going to bring back, because it's just a helpful framework for any opcode in general, right? So I feel like that's one part of the question, and the other part of the question is, like Claire said, like, do we need op stack or other opcodes? Those can be separate conversations, maybe.
Yeah, we have op stack. We didn't get rid of that, so that one we already have. I can give you a list of opcodes that are being re-enabled. But I think it's so. This comes back to Gloria's kind of point. Is there like this cult of Satoshi? Well, the original language was perfect. We should stick with that. And I'm like, yeah, but it's a Schelling point. It's like a obvious, no, we're not choosing favorites. Let's just go back to the original scripting system, which would lead you straight to, yeah, but you have to worry about DOS vectors, right? Because they were eliminated for a reason, so you need to justify them. The opcat proposal sticking to 520 bytes is like is a minimal approach. Like that's sort of minimal. Well, we'll stick with the same. We haven't introduced a new DOS vector because we've got the 520 byte limit, but we'll just reintroduce that. And that may well be that may be the perfect point. I don't think anyone does feel it's the perfect point though. So I'm like, what does it look like if we re-enable everything? And most of these things are just not dangerous, right? Why was op left cut out? I mean, it literally just chops off stuff, right? It didn't, it got a bad rap perhaps, but it was in those set of opcodes that were near opcat, right? So we didn't get a very carefully sculpted subset. We got what we got, so rather than picking favorites on the way back in, just go, well, let's just bring those back. I think that is a reasonable Schelling point, right? And then you do actually want more in script. You definitely want genuine introspection. I think you can't have full programmable money without that. And we've seen examples, I'm not actually a huge fan of vaults because I don't think they make practical sense, in the sense that the vault is the thing you do after you've done everything else, and most people have not done everything else. Like if you're not using an HSM and you don't have a system for observation and signing and all these things and remote Oracle signing off your thing and all this stuff already, then what the hell are you doing? Because you're going to be priced out of doing it on chain. Most people are not asking for their Bitcoin to move slower and more expensively. And I imagine there'll be fewer people doing that in the future. So, but it is a good intellectual exercise to go, what would a vault look like if you were doing it in raw script, right? And most people have shied away from that question and gone, well, we need this specific opcode that does a vault for us and an unvault opcode. And I'm like, well, if you can justify doing that in script, then why can't you do that in script? Like almost anything you can come up with, you go, well, why do you have this boutique use case? Why not make script powerful enough to do exactly what you want? And I think that's a compelling argument to go, well, we have general purpose computing and the original language is supposed to be a general purpose expression language. It's not like Satoshi looked through each of the ones and went, which one of these would be useful in money? he kind of went, let's have a general script language, and then went, okay, which ones seem dangerous that no one is actually using right now, and cut them off. But I don't see, you know, I really dislike the idea that we would kind of pick winners, because my entire career has taught me that, you know, you build these general platforms and people go and do amazing things that you couldn't have really conceived of. And if you try to overly constrict what happens at the beginning, you'll never get there, and you'll never know what you're missing. Michael.
I guess I'm just curious what you think the kind of next steps are from here then, in terms of the great script restoration project.
Right. I get off my ass and post the BIP. Now I have I have some nominal numbers I'm reasonably happy with. Right. I have my weights. I have like, cool, this is how much it should cost for everything. I do that. Along with that, so the very drafty BIP that describes all the restored opcodes, exactly how they behave, exactly what they cost, how the model works, and we bike shit over that a bit, I'm sure. Along with the code to actually implement it. Particularly, the two things I want to release are a nice, maybe probably even pre-compiled binaries for people to run the benchmarks on their own machine. Like, okay, so look at all these opcodes. What's the slowest opcode on my machine, and how bad can it get? Like, if you basically manage to max out the budget using that opcode, how long would that take to evaluate, right? And for some comparisons, what would the worst case signature 80,000, signature validations take? So you can get some kind of idea. That's important. And also the tool that takes a script and will tell you, okay, this can handle a maximum input size of this, and see what you can build with that. Just to provide a little bit of a playground for people to play around with and see. So that's kind of the next steps. There's a whole, obviously, activation political side to this that I'm not. I entered into this journey because I was annoyed that no one else was doing it. Because I felt that this was the work that had to be done if you really wanted to evaluate what script improvements, would look like. And if we wanted to kind of undo some of the damage that was done, it may well be that there's never another soft fork, right? That people are, happy with the way things are or whatever. I also think that some of the proposals have been too timid. I'd like to say, well, if you were engineering from scratch, what would you fix? And I think this is a good answer to that. But, I don't, I have very little insight into how that game would be played. And I suspect there's a lot of soft skills involved and other things that engineers are typically terrible at. And I certainly don't feel that I have the populist meme thing to drive progress on this. So I think the next thing is to present it and see what people do. Like, present something concrete, I mean. Yep.
Cool. I guess tangentially related in terms of soft forks, I'm wondering if you've had a look at or been following Antoine's consensus cleanup work there. Any of your thoughts on that?
Yep. Yeah, that would be my personal preference for the next soft fork. Although, while some of them were obvious, he alluded recently that he had found some more denial of service things that he wanted to fix. So it's not clear to me that stuff is as far along as we had hoped. But yeah, that always struck me as a bit of a no-brainer, right? It's a soft fork that probably should have been done a while ago. But no, I haven't been following it closely, only the occasional optech. Fine. Thank you very much for listening. Yeah, I hope it kind of was somewhat enlightening on where I'm up to. And yeah, I will be posting to the mailing list. And yeah, it's difficult because, of course, I have a real job in the meantime, and family and kids and stuff. But I do try to carve out some time to dedicate to this stuff because I think it's worthwhile and interesting. So yeah, hopefully I'll get to the stage where other people can play with it and forgive me for my C++ skills, which are very rusty. But yes, cool.